All right, our last chapter, solids and materials. We're going to go through this really quick because a lot of the information in this chapter is kind of specialty stuff, and some of it's real cool and very interesting. But at this point in your Gen Chem 1 education, it's really not as important as some of our other topics. So we're going to go through this a little quickly. And your author puts a lot of interesting stuff in here, like X-ray crystallography. Fascinating technique. I love it. It's really cool. But I believe it's beyond the scope of what we need to be covering. So we're going to just skip right through there. A lot of X-ray crystallography, which allows us, by using X-rays, by the way, to determine the structures of molecules, is depend on what we call unit cells. The basic structure of solids. How are solids packed together? Recall the atoms or the molecules in a solid are very close together and they're in a very regular form. And this regular form is called a unit cell. And so if you had a bunch of atoms kind of packed in there this way, the unit cell would kind of look like this. And there are a number of designs for unit cells like this. The interesting thing is the unit cell itself comes from the various atoms and how they arrange themselves. But when you crystallize molecules, when you take something that's dissolved and turn it into a solid crystal, it turns out the shape of the overall crystal is going to be the same shape as the unit cell it came from. So that's kind of interesting, but not interesting enough for us to really worry about it. Okay, the types of unit cells that you can find, here's a nice table of them. Simple cubic, body-centered cubic, face-centered cubic, has all sorts of interesting information, but not for us. We're just going to skip this stuff. But it is through these unit cells that you could figure out the sizes of atoms and things along like that, radius of atoms. So we're just going to keep going through here. And then it goes into how the various layers will pack on top of each other, the closest packed structures. You have down at the bottom here, you have hexagonal close packed, you have cubic close packed, and I don't care. So we're going to keep going. Now here's probably the most important part of this chapter. This is the stuff you're going to get tested on. The types of crystalline solids and essentially their properties, particularly melting and boiling points. So if you have a solid compound, if you have a solid, it can be broken up into different types of solid. One is molecular solid. This would be like water forms ice as a solid, solid sugar, where you have individual molecules themselves, covalently bonded molecules, arrange themselves in a solid. And these molecular solids tend to have fairly low melting points. I mean, ice, well, not that low. Well, yeah, ice, 0 degrees is when it melts. Yeah, not a problem there. Sugar, a little bit higher melting point, but these are your standard organic molecules like sugar or ice, all these molecular solids. Ionic solids, this is like sodium chloride. They have high melting points where you have a sodium ion, then a chloride ion, then a sodium ion, then a chloride ion. You have ion-ion forces attracting them together, so they really, really don't want to break apart. They have high melting points, these ionic solids. And then you have atomic solids, where the structures are composed of kind of individual atoms. And you could have non-bonding solids. These are like your noble gases, like helium and xenon. And note, the only forces that hold noble gases together are the dispersion forces. So they really, well, they're gases. They only have dispersion forces. But you can form solids, especially with the larger ones like xenon. But they do have very low melting points because the dispersion forces are our lowest forces. You have metallic solids. They're kind of held together by metallic bonds, and they have variable melting points. Some metals melt kind of low temperatures, some melt at higher temperatures. And finally, we have network covalent solids. These are atoms held together by covalent bonds in a three-dimensional network of atoms. And we're going to take a look a little bit further, a little bit into these metallic solids, and we're going to look at these network covalent solids. All right. Metallic solids are interesting because metals, we know they conduct electricity very well. They conduct heat very well. And metals really can be thought of, even though it's a bunch of atoms together, like a bunch of aluminum atoms close together, they really behave as if it's a bunch of nuclei, positive charged nuclei, in a sea, this big old sea of electron density. It's almost as if the electrons on any atom, they're kind of free to flow amongst all the other atoms. Because of this way of electrons being very free to move, because it almost seems as if it's just a bunch of nuclei in a whole sea of electrons, it's, wow, man, it's almost like the opposite of the Thompson plum pudding. Remember that one? Was the electrons were the raisins and the positive charge was the sea of positive charge, the pudding of positive charge. With metals, one of the best ways to look at it is the positive nuclei are the raisins, and they're in a pudding of negative charge. That's kind of how metals operate. The electrons are free to move, so they conduct electricity very, very nicely. And so that's one way to look at metals and how they behave. Let's see, we've got our ionic solids here. That's some fun stuff. Our network covalent solids. A prime example of network covalent solids is when we deal with carbon. Now, there are two allotropes, main allotropes of carbon. One is graphite, like you will find in your pencils. They are sheets of carbon atoms. Each carbon atom is in a hexagon pattern here. And they're like sheets of carbon atoms that are just kind of held together by dispersion forces. So what that means is if you have your pencil and you drag it across a piece of paper, we call that writing. But when you drag the pencil across a piece of paper, these little sheets of carbon atoms just kind of get sloughed off by the friction, because what's holding this sheet on that sheet? Just dispersion forces, and they can tend to be a bit weak. And so this sheet will come off, then the next sheet, and that gives us our pencil line on the paper. Diamond is different. It's a little tough to tell from this diagram here, but you have carbon bonded to this carbon, this carbon's bonded to the original one and three others. Each one of these carbons is bonded to four other carbons in this whole network of carbons. So you can't just pull out one carbon because it's bonded to four other carbons, and each one of those is bonded to four carbons, and each one of those is bonded to four carbons. That makes network covalent solids tend to be very, very tough, very, very hard. Diamond is the hardest thing known because of this network covalent arrangement of carbon atoms. Other things, if you're in construction, boron nitride is very tough. It's a very tough material that you put on drill bits and things like that to break through things, because it's very, very difficult. It's this network covalent solid. Quartz is a network covalent solid, a mixture of silicon and oxygens. Right here, we've got these silicon and oxygen tetrahedral mixtures, or tetrahedral arrangements right here in this network, this three-dimensional network, that makes it quartz very, very hard, very tough things. All right, and really that's it. Now the book goes into some other interesting thing about ceramics and glass and how that's made. A little bit more about metals, polymers, but we're not going to deal with polymers until organic chemistry, so don't worry about those. And that's the end of this chapter. So the main thing, the main issues we cover in this chapter is really just this table here of the properties of these solids, the different types of solids we have and their properties. So that is it for this chapter, and that is it for this semester.